Thank you very much for this nice introduction and for the invitation to come here to KAIST. I've spent now almost 2 weeks, had a very nice time doing math and counting side dishes. It's getting more and more every day. So today I'll talk about Powersum decompositions of symmetric tensors. So I'll try to avoid being too technical. I'm not going to. I cannot promise being untechnical all the time, but I'll try to as far as I can. So let's see if I get this to work. Yes. So let's consider the problem. So I have a symmetric tensor, and I think of that as a homogeneous form, a homogeneous polynomial in a number of variables. It has a certain degree, say d. And now for some reason I want to write this as a sum of powers. Think of that as a simpler way of writing it. You know, normally we just use a monomial basis and write it as a sum of monomials with some coefficients. Well, I insist on using powers. So the Li here are linear forms. So the first question is, of course, is it possible? Is it actually possible? And well, if it is possible and you have such a presentation, it's called a boring decomposition of length r. R is the number of linear forms that you need. Okay. And so we generalize this question: is it possible to say what is the smallest r, if possible, that you need for a polynomial f? The smallest r we call the rank of the polynomial. Okay? And the next question is, for this smallest r, how many decompositions are there? Is it possible to do it in different ways? So classically, and now I mean by classic, in the 19th century, this was attacked as a problem of finding some canonical form for the homogeneous polynomial. If there was a unique way of writing this as a sum of powers, I thought they were thinking of this as a canonical form. And that is possible in some cases, and most of those cases were sorted out in that century. So more recently, it's the structure, how many, and if it's infinitely many, the structure of the set that has been the focus. Okay? So let's start with the case, the first non-trivial case, right? The trivial case, of course, is linear form. A linear form is a power of a linear form, and there is everything you know about that. So let's go to the next case. That's for quadrics. So if you have a quadratic form, the rank is equal to the rank of the associated symmetric matrix. Right? You have a quadratic form, and you can write this as such a product of matrices where the A is a symmetric matrix. And the rank, as I defined it in the previous page, was as a sum of squares. If you write that as a sum of squares with this matrix, you get a diagonal matrix, and then the rank is exactly the number of non-zero elements on the diagonal. So the rank is the rank of that matrix. Okay. So that's the first question. Then is easy. You can write it as a sum of squares. remember we are over C now, so you have plenty of room, right? But now let's look at this slightly more geometric to see how many ways can you write this as a sum of squares? How many ways can you write this as a sum of squares? So I want to describe this slightly geometrically also. So the big Q is the hypersurface in projective space defined by this quadratic form. And then if you have a power, so a sum of squares for the presentation, sum of square presentation for Q, then each of these Li define a hyperplane, and the union of these hyperplanes, n hyperplanes, is called a polar simplex. A polar simplex. Because you know from, maybe you remember this from high school, polar of a conic. So I'll remind you about that in a moment, but for when you have a quadric at any point in the space, then there is looking at the conic or the quadric from that point, you see the horizon of the quadric. That is a hyperplane section of the quadric. So it's a section of the quadric with a hyperplane. And so these are all such hyperplanes. And then if you take the first n minus 1 of them and look at their intersection, you get the point. And the last one is then the polar hyperplane to the intersection of the first n minus 1. Okay, so that's and you do that for any, and you get the polar simplex. So we'll do this in the plane now to see more clearly. In a moment we'll do it in the plane to see what this is. So anyway, the polar simplex, I can think of that, well, on the one hand as a set of hyperplanes, n hyperplanes. In the dual space, this is n points. The dual projective space parameterizes hyperplanes, right? So the n hyperplanes become n points in the dual space. So now I look at the set of all polar simplices, look at the corresponding set of points in the dual space as a family of sets of points, and I've tried to find some compactification of this. And the natural place to look for this is the so-called Hilbert scheme. Hilbert scheme of that dual space. That's just a parameter space for finite subsets in this case. And inside this Hilbert scheme I can take the closure and get a manifold or something of this sort, as we'll see. So that's going to be the definition of that. So we want to see what are the global properties of this set of polar simplices in this case. Okay. So the crucial thing is to see not just the polar simplices, but what happens when I compactify. What are the points that I need to add? What are the things on the boundary? What are the things on the boundary? So let's try to see the whole story for conic sections. So if you're a little bit lost, now you can jump in again. Because now we're in the plane, and here is the quadratic hypersurface. Here is the conic. Right? And now I've drawn the black triangle here is a polar triangle. It's a polar triangle. So how do I get that? Well, I start with one point this is chosen randomly, chosen this point, and I look at the conic from that point. What is the horizon? That's the horizon is these 2 points. When I look at the conic from there, I just see the interval ending at these 2 points, right? And through these 2 points I have the polar. This is the pole, and this line is then the polar of that point. That's what we did in high school, or should have done in high school. Okay. Now I take my second point over here on the polar of the first. And then the result is that the polar of the second point is a line that passes through the first pole. See that? If I take this, any point here, then the polar line will pass through the original point there. So this is the symmetry in the situation. And now when I have chosen these two, the third point is fixed. And the polar of that point is this line over here. Well, I cannot use the imagery of a horizon when I'm inside, right? But you actually do this easily with the equations, and then this is a line outside. So in the complex plane, then this will also intersect in the tangency points from this point. Okay? So this is a polar triangle. And you can see from this picture also how big a family you have of polar triangles for the conic. Because the first point was chosen freely. I have 2 parameters, any point in the plane. And then the second point I choose on the polar line of the first. So that's 2 plus 1. And then the third point is fixed. So I get 3 dimensions. 3 dimensions. I get a 3-dimensional family. Okay. So now I'm going to see what happens when things come together. What could happen? Well, if I go closer to the curve, I get this situation here. So here I start again with this point outside, and I get this line, polar line, and now I choose the point on the conic. If I choose a point on the conic, then the polar line is the tangent. And then the intersection between the tangent and this other polar line is E itself. So I have to do this twice. So somehow what used to be an honest triangle has been reduced to 2 lines. But one of them, the tangent line here, counts twice. Counts twice. Okay? And this kind of situation, of course, you'll have all around. And I have the double line here. And the first line here, this will move around E as D moves along this line. So I have a whole pencil of different degenerate triangles with that double line. Okay? And the worst possible thing that could happen is that they all come together and you get the triple. So these are the degenerations. This is what happens on the boundary. So this is one such thing for each point. So that's a 1-dimensional family of such things. And the previous is a 2-dimensional family. One, the double line here, and then a simple line moving in a family. So that's the whole boundary. So now we'll try to describe this after having seen somehow the geometric picture of these ways of writing a conic as a sum of squares. We'll go to the algebra. Well, we'll stay a little bit, I'm sorry, I will stay a little bit more at the geometry. So, we think of the space of linear forms as a projective plane. So the space of linear forms modulo scalars, we think of that as a projective plane. And we think of all the conics, these are quadratic equations, as a P5. There are 6 coordinates, so up to scalars, that's a P5. Now there's a natural map of the linear forms into the quadratic forms, taking the square, L to L squared. So inside P5 I have all the squares. This is called the Veronese surface. And inside this P5 I also find my conic section, my quadratic form, as a point in this P5. So now what I do, I project this Veronese surface of squares down from that point down to a P4. Okay? And I'll see what happens. Then the following are equivalent. If I have 3 linear forms, and this upstairs here, if that is a polar triangle, then I know that the little q is the sum of those 3 squares. So if I think of all these elements as points in P5, I know that q lies in the span, linear span of these 3 points, these 3 squares. That's the same as saying that q can be written as a linear combination of these 3. And since I'm over the complex numbers, I can put the coefficients inside the squares, and I get the sum of squares this way. So that's 1 to 2. And now when I project these points from the point Q, well, if Q is in the span of the 3 points and I project from Q, the 3 points will become linear. They will become collinear. They lie on the same line in P4. So they used to span as 3 points. They used to span a plane in P5. After projection, they become collinear. They are on the same line, because your projection center is in the plane spanned by the 3. Of course, they're still on the surface that comes along, for the projection. So this way, you actually get a trisecant line to that surface VQ, the Veronese surface projected into P4. And actually, the whole family of polar triangles correspond precisely to the trisecant lines of VQ this way. So this means that I don't need to go to the Hilbert scheme, I can just go to the Grassmannian. So this family of polar triangles, that's what this says, has a map into the Grassmannian of lines in P4, or the Grassmannian of 2-dimensional subspaces of a 5-dimensional vector space. So that's my notation, G25. You can think of this as lines in P4 or 2-dimensional subspaces in P5, in the 5 space. Okay? So again, let's look at there's another interpretation of the whole thing here. We can think of the P4, just to describe this, we can think of the P4 as all binary forms of degree 4. Well, think of that as all polynomials of degree 4 in one variable. You can homogenize, of course, but just think of them as all polynomials in one variable of degree 4. You have 5 coefficients. And up to scalars, this is just a P4. Now you can sort them into those polynomials that have 4 different roots, those that have 3 different roots and one double root and 2 simple roots, etc. If you look at all those polynomials that have 4 tuple roots, that are 4th powers of linear forms, that form a curve inside there. And those polynomials that are squares or quadratic forms, they form a surface that contains the first curve. So that's this stratification. There's C4 into S4 in P4. And now my surface VQ that I had in the previous slide can be identified with this S4. Can be identified with this S4. And so my set of polar triangles can be seen as the trisecant lines to this surface S4. And in this interpretation you can see the degenerations because you have the particular curve C4 and the tangent lines to C4, that's actually just the worst degenerations that we saw. Just the one parameter family of triple lines we saw in 3 slides ago. While the tangent lines to S4 that are tangent at a point on C4, that's the surface of lines, that's the first degeneration that we saw. So here we have a geometric picture of this whole thing. And in the Grassmannian, those tangent lines to the rational curve, to the curve C4, they are, as like a Gauss map, you have a curve in P4 and you take every point is mapped to its tangent line as a point in the Grassmannian. That's the Gauss map. So the image of this Gauss map is this C cube. And the result is that if you look at the Grassmannian of G25 and look at the linear span of that curve, that is actually a P6, and the intersection of these two is exactly our 3-dimensional variety of polar triangles. That's exactly the 3-dimensional variety of polar triangles. And this was shown by Mukai in the late 80s. So I wanted to go through the details of this here because this is where there is some. It has all the things that you really need to see the rest. And then I'll go quicker, just show the results in more general setting. But to do that, I should also introduce the other part, the algebraic part of this story. That goes back to Sylvester. Also, that part is something building on things we learned in high school. We learned how to differentiate. So now, when I take 2 copies of the polynomial ring, S and T, and then I let this T act on S by differentiation. So any y here, y applied to a polynomial f is yi applied to polynomial f is differentiating with respect to xi. And if I take a polynomial, then I just take the corresponding differential form of as the polynomial and apply it to f. And if you do that, you see, if you have a linear form in S, in the x's, and take any polynomial, say of degree d, in the differential operators, and you apply that to the linear form, to the dth power here, then what you get is the evaluation of g at the point corresponding to the linear form for some lambda, but this lambda is independent of g. That's the point. Okay, and so we say that a differential operator g in T is apolar to f if it has degree less than or equal to the degree of f and still kills it, annihilates it. This is certainly possible. If you have a polynomial f in x naught up to xn minus 2, and then you apply x, y and minus 1, you get to 0, right? For instance, this is certainly possible. You can have forms g that kill f even though g is of smaller degree. So this apolarity given by this differentiation means that you can think of the linear forms of S and T is as dual spaces, and so Pn minus 1 dual is natural dual to Pn and is naturally the linear forms in T. And the apolarity lemma, which tells you somehow how to get to these decompositions that I started with in the beginning, and that we can I've just seen so far for quadratic forms, but can be used in general, is that if you take now a collection of linear forms, L1 up to Lr, then f can be expressed as a linear combination of those linear forms if and only if every polynomial g in T that applied to these Li to the degree g's power is 0, so they eat them, so to speak, they kill them. If they kill all of these linear forms, then they kill f. So this is an if and only if statement. F can be expressed this way if for every g that kills all the Li, it also kills the f.
Professor.
Yes?
Also the relation, the degree of g.
The degree of g.
D.
This is the g. So it doesn't depend, so f has degree d, right? But here I'm just applying this to these forms, and I take this to the degree d, g, to get what I had in the previous slide. You see here, g, I applied g to this here when g is of degree d, right? So that's the same here, when I want this to be the degree of this one, okay? So now these two objects that I saw down in the previous slide, they're ideals. So the g that kill all these linear forms and the elements g that kill f, they are both ideals in T. So I could express the same as saying if I have a finite set of points, if the ideal of the set of points are in the annihilator of f, then f can be expressed as sum of powers with these linear forms. Now I extend this to subsets where the points come together. Subschemes is kind of thick. The subschemes are simple points, or they are thick points where points come together. Or they are bigger varieties also, but we'll also only use them for finite set of points, or finite thick points. So now I'll just briefly say the results on the quadrics in general. So we saw the quadrics, the first example, but now for higher rank, you have a very similar picture. You have a Grassmannian embedding of this variety of polar simplices. If you extend this to all apolar subschemes, also thick points in general, there is an inclusion, and this is also included in this Grassmannian. In the case that we saw, these two are the same. For conics, these two are the same. And this here is the higher dimensional analog of this Gauss map that we saw with C4 into P6. You have this curve that was embedded with its tangent lines into P6. This is a higher dimensional analog of that. And the span of that Gauss image intersects the Grassmannian precisely along this big thing VAPS here, all the apolar subscripts. And the point is that if the rank is big, if the dimension of the quadric is big, then there are more apolar subschemes than just the limits of the smooth ones, smooth simplices. So this becomes a reducible thing. So things go bad, you know. And if you just look at the polar simplices, this is a rational variety of this dimension. This is what we counted precisely when n was 3. And it's very similar count to get dimension n over 2. And it's a nice variety in the first couple of cases, but as soon as n is bigger than 5, it's actually singular. It's badly singular, this variety. Okay? So now, what is the story for if you go beyond quadrics? What are the results there? As I said, starting with Sylvester in the 19th century, they looked at canonical forms. And when this was taken up again in the 80s, Mukai looked at the varieties, the manifolds, the whole sets of different decompositions. And as we just saw with conics or quadrics, you get a nice big set of different decompositions. But let's see what happens for a higher degree, what the results are. So first, if you start with binary forms, just homogeneous forms in two variables, then the annihilator, as I described it in the dual ring, is actually generated by two elements. It's so-called complete intersection, and the degree, the sums of the degrees of those two elements is equal to the degree of f plus 2. Now, the lemma said that that f can be written as such a decomposition if and only if the ideal of those points, well, if you have a number of points on, well, we're two variables here, so we actually on P1, we are on a line. We have points on the line. And the ideal of forms that vanish on points on the line are generated by just one polynomial. The product of the linear forms, one for each point on the line. And so what we're asking here is that defining polynomial for that set of points lies in the ideal. So if we ask for the minimal number, we simply go to the smallest degree of those two. This just means that G can be written as a linear combination of those two, where the coefficients are also polynomials. So the smallest degree is what you get if you take the smallest degree of those two. But that, if you take that, then you might be unlucky. Maybe that smallest degree is not square free. If it is square free, that's the rank. If it's not square free, then you have to go to the next one, all the way up to the next one. So this was all described carefully by Sylvester in the 1850s. So because of this, well, there is a modern definition of cactus rank, where we just don't think about counting points. We also allow these thick points, and then you ask for the minimal length. So in that case, the cactus rank of a binary form is exactly the smallest degree of the two, independent of whether this is square free or not. But anyway, the cactus rank is always less than or equal to the rank. And in this particular example, this is a form. This is a form of, this is a binary form of degree D. Back to the original question, can I write this as a sum of dth powers of linear forms? And this analysis here says, well, first of all, the apolar ideal, the annihilator, is generated by these two elements. If I apply y0 twice, I kill this guy. If I apply y1 d times, then I also kill this guy. So these are the generators. But the first generator, the one of lower degree, is not square free. It is a square. So to get something square free in this, I have to go all the way up to degree d. So the rank is d, while the cactus rank is just 2. That's the degree of this guy. Now, so this example was a very special form. A general form, then the 2 degrees are as even as you could get under the condition that the sum is degree of f plus 2. So therefore, well, in general, there is a statement here about the rank for forms in any number of variables on any degree. But the statement is about the form of the rank of a general form. Of course, you can always find forms of degree d as just a sum of 2 or 3 linear powers of linear forms. But the general form, how many do you need? And that's exactly what is out of this statement here. This was proven in 1995 by Alexander and Hirschowitz. And the formula is some general formula here with a few exceptions. And these exceptions were all known to the around 1900, 1905 or so. All those exceptions were known. But to prove that there were no one else, this was the result of this theorem in 1995. So this is a rank for the general form. Special forms might have higher rank, as we saw in the previous slide, and that has been analyzed only in a very few cases. What is the absolute upper bound? If you allow points to come together and you look at the length, then you have better bounds, you have lower bounds. You compare, so this is a bound for the cactus rank, but here unfortunately is only an inequality here, but they're less than or equal to these numbers, and these numbers are definitely smaller than the bounds given on or the ranks given on the previous slide when d and n is big. So this means that when d and n is big, then you're more likely to have this kind of thick points contributing to the rank earlier than the just simple points. And so the question is this really equal or not? Is this bound sharp? This is not, but there's a little bit of progress on this in some work on cubics in a few first cases. It shows that this is actually sharp. But this is actually a wide open question. Wide open question. Now for a couple of other cases before we go to the families. So here's another example that you might think of, if you have a monomial. If you have a monomial, what is the rank of a monomial? Try to write a monomial as a sum of powers of linear forms. So in this case, this apolarity business can work out. And so this was worked out a couple of years ago. And the cactus rank, if the monomial has powers d0 up to dn, and these are in growing order, then the cactus rank is d0 plus 1 up to dn minus 1 plus 1. While the rank was then proven to be less than or equal to d1 plus 1 up to dn plus 1. So you just shift it a little bit, right? Of course, if they're all di's are equal, you get the same. But if not, then this is higher than this one there. Right? Well, the cactus rank was shown to be equal to that thing, and the rank was then shown to be equal to this by Carlini and Catalizano and Jaramita, also in 2011, a little bit later than the other thing. So now finally, in how many ways? How many ways can you write a sum? Has a polynomial as a sum of linear forms of the minimal number? And well, first of all, the dimension for the general f comes from the bound that we had earlier here, the Alexander-Hershowitz theorem. So that's the start, but the precise structure is then worked out in some other cases, and that's all summarized here. So in the first case here, we actually have, well, when I say that this VSP is a point, it simply means that the general form with this degree and number of variables has a unique presentation as a sum of these powers. There's a unique way of doing it. And that is the case if the form is binary and of odd degree. So cubic binary form is uniquely a sum of two cubes. If a general cubic form in two variables is uniquely a sum of two cubes. Also, if you have a quintic form in three variables, this is uniquely a sum of 7 fifth powers of linear forms. 7 fifth powers of linear forms. And this case here, as a cubic surface or a cubic in 4 variables, can be written as a sum of 5 cubes in a unique way, the general one. Okay? So this is where you have a canonical form. And now here, if you have a binary form of even degree, then the 2 generators of the annihilator have the same degree, so you choose any element in that degree there, in that ideal of that degree, and you get a presentation. So that's the P1. So at P1, you have a P1 of different presentations if you have a binary form of even degree. And if you have a cubic form in 3 variables, you get a P2 of different presentations. If you have a cubic sextic form in 3 variables, then you get the K3 surface. Then you get a Fano threefold. We saw that for a quartic in 3 variables. You get a Fano fivefold for a cubic in 4 variables. And finally, a hyperkähler fourfold for a cubic in 6 variables. And so that summarizes the results there. And this has really been a way of getting of presenting these varieties here in from a completely different angle than before, and actually giving you a surprising correspondence between moduli spaces. Moduli spaces of forms on one hand, and moduli spaces of certain varieties on the other hand. So in this case here, you get the moduli space of genus 3 curves corresponds to, or plane quartic curves. So there's a birational map to that, from that to the space of Fano threefolds of genus 12. Okay, so I think that's a good part to stop, because now also my 50 minutes are over. Thank you.